In a previous video, I showed that e to the 2 pi I can be proved to equal 1 using series. I wanted to come back and just do kind of a more formal showing of this. This is the idea of Euler's identity. And Euler's identity actually shows that e to the pi I is equal to -1, okay? And I think normally they write it like that, though. E to the pi I plus 1 is equal to 0. And again, it's a mind-blowing concept in the sense that the formula unites 0, 1, I, pi, and e all into one relatively simple little formula, okay? So it turns out that complex numbers can actually be written in the form. So we have basically cosine I sine form. R cosine of theta plus I sine of theta. And it turns out that you can actually write cosine of theta plus I sine of theta as e to the I theta power, and then of course you're multiplying by r. And so for example, let's say I had an imaginary number. Let's say I had something like, well, let's just say I had something like the number 10, okay? No, let's not do 10. Let's do something like 3 plus 3i, okay? You could write that in cosine I sine form as the absolute value would be 3 radical 2, and the angle measure would be 45 degrees or pi over 4. So you could write that as 3 radical 2 cosine of pi over 4 plus I sine of pi over 4, okay? What this is implying is that you could write this using an e. You could also write it as the absolute value times e to the I times whatever your theta is. And my angle measure in this case was pi over 4. Actually, you'd probably write that as pi over 4i, okay? That these two things are equivalent, okay? So that's actually what I'm going to show here is this relationship. Yeah, I kind of use it a lot in high school math, but I still think it's a pretty cool little proof. So the idea comes back to something very simple. So I'm going to take, again, I'm actually just going to show that e to the I theta is equal to cosine of theta plus I sine of theta. You can multiply both by r. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on, okay? If I wanted to write this as e to the I theta, I could just substitute an I theta in for each of these positions. So I've got an I theta there, I've got an I theta squared, I've got an I theta cubed, I've got an I theta to the 4th, let's go a little bit farther here, an I theta to the 5th over 5 factorial, and I theta to the 6th over 6 factorial. And I can try to simplify all of this. So I squared is -1. So I'm going to write this as minus, actually I'm going to factor out the I here. So I'll write this as theta times I, and then I'm going to have minus theta squared over 2 factorial. This is going to be minus theta cubed times I, okay? I to the 4th is going to be 1, so this is just the same thing as theta to the 4th. I to the 5th is I, so this is going to be theta to the 5th times I to the 6th is -1, which is going to be the same thing as minus theta to the 6th. Then we kind of go on from there. So if you saw my previous video, I broke up the imaginary parts and the real parts, and I kind of looked at those separately. And so the real part here is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. And then we have an imaginary part that is theta times I minus theta cubed over 3 factorial times I plus theta to the 5th over 5 factorial times I, and so on, okay? I factor the I term out of each of these, all right? And if you put all this together, what do you get? Well, this is basically 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. That's just the even-termed alternating series. That's cosine of theta in this case. I used a theta instead of an x, okay? Down here, notice it's odd terms. We've got basically x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. That's the sine function, okay? But the whole thing is being multiplied by I, okay? And so what I have shown here is that e to the I theta is the same thing as cosine of theta plus I sine of theta, okay? And of course, if I wanted to take r times e to the I of theta, I could take r times cosine of theta plus I sine of theta. So this links those two ideas, okay? And basically says anything you can write in cosine I sine form, you could also write using this setup here. So again, if you have something with a magnitude or an absolute value of 10 and an angle measure of pi over 3, that'd be the same thing as 10e to the pi over 3i. Okay, so kind of a cool idea. Coming back now to Euler's identity. So if this is true, let's see what that tells us about Euler's statement. Euler calculates e to the pi I, okay? E to the pi I, of course, is 1 e to the pi I. So our absolute value is 1. The angle measure is pi. So pi radians, same thing as 180 degrees, you're popping up over here at that value, okay? That's -1 plus 0i. That's the value -1, okay? And so we can show that e to the pi I is equal to -1, and then obviously -1 plus 1 is equal to 0, and that is how you can prove Euler's identity using series. So pretty cool. Again, a little bit abstract, but really cool that as you floated through school, all of these numbers, 0 and 1 and pi and I and e, all come together in this identity. Neat stuff.